Section 3 of Chapter 3. So this part we will talk about the differentiation rule. So that means after this section, we can just rely on some formula, some rules instead. Just like before, we just rely on the formal definition for the differentiation or for the derivative. But right now, if we have the differentiation rule, if we want to get the derivative, it will become more efficient. So let me just show you several rules. The rule number 1 is if f of s is a constant function, then when we just differentiate, the value is 0. I believe this part is very simple because you also can follow the original definition for getting the derivative, but also you can just try to use the concept about the derivative. Did you still remember when we just say we want to get the derivative? It's about that we try to get the slope of the tangent line. So for a constant function, f of s is equal to c. That means the curve will be just like a horizontal line, right? For the horizontal line, the slope, what is the slope? 0, right? So no wonder when we just differentiate, the result is still the same as the slope of the curve. Since it's a horizontal line, so the slope will be 0. So it's quite intuitive, right? Okay, the second rule is, rule number 2 is we try to differentiate s to the power of n. So the result, I believe, if you just learn calculus before, you know the result should be s times x to the power of n minus 1. But especially here, we just focus on n is a positive integer. So right now, we just focus on n is a positive integer. And later on, we will gradually extend the idea from positive integer to negative integer. So that means all of the integer. Then we will gradually go to like rational number. Then finally, in chapter 7, we will know that the number n here also could be a real number. Okay, but at this moment, we just focus on n is a positive integer. So for this part, I can give you a simple proof about this part. When we just talk about f prime x, that means here f of s is x to the power of n. So when we just try to get the f prime of x, that means going back to the original definition, that will be limit z is approaching x, then f of z minus f of x over z minus x, right? Did you remember we have two definitions for f prime x? One is limit h is approaching 0, f of x plus h minus f of x over h. The other type is limit z is approaching x, f of z minus f of x over z minus x. So for this part, we can just trying to get limit z is approaching x, then z to the power of n minus s to the power of n over z minus x, right? So, but for this part, we can decompose it as z minus x times z to the power of n minus 1 plus z to the power of n minus 2 times x, blah, blah, blah. Here, z times x to the power of n minus 2 plus x to the power n minus 1. You can find this one times, here, this one times all of them, then we can get back to z to the power n minus x to the power n. So with this decomposition, we can just cancel this term and also this term. So finally, the result will be limit z is approaching x, then z to the power n minus 1 plus z to the power of n minus 2 times x, then blah blah blah, z times x to the power n minus 2 plus x to the power n minus 1. So after we just use x to replace z, then finally we can find, okay, here we can get 1x to the power of n minus 1, and for this part, when we use x to replace z, we can get s to the power of n minus 2 times s. So we can also get another x to the power of n minus 1. So for each term here, also here, we always can s to the power of n minus 1. But in total, we will have n terms. So finally, we can get the result will be n times x to the power n minus 1. So in the future, if you want to differentiate x to the power of n, you always can use this formula to get the answer will be that will be n times x to the power of n minus 1. Okay. So this is rule 2. So is that okay? Okay. So for the rule 3, if u is a differentiable function of x and c is a constant, then we can get, when we differentiate c times u, then we just simply move the constant out of them. We can get c times dx d over dx u. So that means if you have any constant here times a differential function of x, you can just simply move the coefficient out of that. Then we can get the result is just like this. This is very simple. You even can use this definition to get the result. So we will just bypass this part, bypass the definition. Then rule number 4, then if we have two functions, u and v are also differential functions of x. So that means we have two functions, u and also v. Then when you just differentiate u plus minus v, then you can differentiate these two terms respectively. Then finally just adding them or subtracting them together. So you can please just notice that here only addition, subtraction work. But in the past, did you remember limit theorem? For limit theorem, you always can, here could be 4 operations: addition, subtraction, multiplication, and division, right? But for differentiation, it is only for addition and subtraction. 在极限定理的时候，我们有讲过4个，对不对？这个要区隔一下哈。 极限定理的时候，在算极限的时候，如果这是极限，两个你要去算极限的时候，加减乘除可以个别加减个别做完之后再做加减乘除。可是，在微分的时候不行哈，只有加跟减可以，乘跟除有点复杂，等一下要请大家记下来。所以这要做一个区隔，不一样的哦哈。Okay, so this is for the rule of 4. Then, okay, I can give you a simple example. For this part, if the question just asks you, does y is equal to x to the power of 4 minus 2 times x to the power of 2 plus 2 have any horizontal tangent? Actually, this question is not, this problem is not that hard, but why I just illustrate here, because you need to understand the question first, and then you can know how to solve it. So in this case, it just asks you if this function have any horizontal tangent. So what is horizontal tangent? Horizontal tangent, that means, can we have any place for this curve? Its tangent line is horizontal, right? So, for example, based on this, you even can draw the curve just like this one, going down and up, then going down and up again, right? So if you try to draw it, you can get the curve. So when the question asks you, can you just get any horizontal tangents? And if so, where? If so, please tell me where. So once you just draw it according to this function, then you can find it just like this one. So this question just asks you, can you just find the horizontal tangent? So that means this is tangent, this is tangent, but especially this is horizontal tangent. This is also horizontal tangent here. This is also horizontal tangent here. So if you can find horizontal tangent, that means at that point, is the derivative should be 0. So if we want to find somewhere which can just produce a horizontal tangent there, what we need to do is we try to differentiate it and find where can cause it to get a 0 slope. So based on this, we can try to differentiate y so that we can get differentiate s to the power of 4 minus 2 times 2x to the power of 2 plus 2, right? Okay, we are trying to differentiate it. And then if you want to differentiate it, you can see this is an item, this is an item, this is an item, right? Through addition, through subtraction. So that means if you want to get the result, it will equivalent to getting the result for this one, right? Minus this one, minus plus this one, right? This part just simply follow rule number 4. We just use rule number 4 because if you want to differentiate two terms added together, that means you just differentiate each term individually, then adding them together or subtracting them together, right? So we just simply apply rule 4. Then you can get the result from here. You can convert from the left-hand side to the right-hand side. So we can just go back to getting the individual parts first, right? And as for this part, you can see, you can also apply for the previous rule. For example, for the first term, what rule you can apply? Rule number 2, right? So for this part, you can just use rule number 2. And for this part, you can just simply move 2 to the front end. So you will apply rule number 3. You will use rule number 3 and also rule number 2, right? Because eventually you need to differentiate s to the power 2, right? And then the last term here, we are trying to differentiate 2. So what rule we will apply? Rule 1, right? Rule 1. Here, if it's a constant, we can apply rule number 1. So I really like this example because, you know, this example is not that hard, but it contains several concepts about the rule number 1 till rule number 4. So 1, 2, 3, 4. We all of rules we learned so far can be applied to solving this problem. So that the result will be, okay, 4 s to the power of 4 number 1 minus 1 minus 2 s times 2 times 2 to the power of 2 minus 1 plus 0. So finally, we can get the result will be 4 to the times x to the power 3 minus 4x, so that we can continue to decompose it as this one, right? So finally, we can get this one. And then we're trying to make it become 0, so that we can get s either is equal to 0 or positive 1 or negative 1. So after you analyze it, you can get these 3 numbers. So 0 will be here, right? Positive 1 will be here. Then negative 1 will be here. So totally, you can find 3 points where you can have a horizontal tangent there, just like here. Okay, so this part is also very important, because if you can find any tangent line which is horizontal, you can find it is possibly we can get an extreme value. Here is a comparative minima value here. Here we can get a comparative maxima value here, and here also for minima, right? So in chapter 4, we will apply this idea to get the extreme value, and also see where we can get the extreme value. So here is just a step 1, try to differentiate it, and then try to find where we can have a horizontal tangent. Okay, so this is a very good example I want to show you. And then we can continue to find the rule number 5, that we are talking about the derivative products rule. So here you can see product here. So rule number 4, we just talking about addition and subtraction. We did not face the problem about the product. The term when they just product together, we didn't talk about how to get its derivative, right? So here we just want to get it. So here we also face 2 functions times together, we try to get its derivative for the multiple together term here. So based on this, please just also go back to the original definition. So that's why I just told you that when you want to derive any formula, don't forget its original definition for the derivative. So in chapter 2, in the section 2 of chapter 3, we find its original definition. It should be limit h is 0.0 u of x plus h times v of x plus h minus u of x v of x over h, right? Because at that time we just learned f prime x could be limit h is 0.0 f of x plus h minus f of x over h. So always keep this definition in your mind. If you can directly apply the rule to get the derivative, you always can find the answer through its original definition. Okay? So if we want to get this one, we also go back to its original definition. We also follow a rule, which is limit h is 0.0 u of x plus h times v of x plus h minus u of x times v of x, right? So we just continue to expand it. We can just limit x is 0.0. Then we already have this term, u times x plus h, v times x plus h. So in the middle, we can just subtract in one special term, u of x plus h times v of x, right? Because you just add this addition term, we need to add it back. You just subtract the addition term, so we need to add it back with u of x plus h times v of x. Then we still have u of x times v of x. So it's easy, right? Adding one special term and subtract this special term, so we can cancel and go back to the original. Right? With this, we can put this together and put this together. So don't forget, at this moment, we just facing the operation of getting the limit. So we still can apply the limits rule for these two parts. We can just separate them with this red part and also this original part. Origin part. Huh? Which one? U v of x plus u plus h v of x. Oh, this one, yes. Okay, thank you. So this should be, yeah. Okay, let's try to find the eraser. Okay, here. Yes, correct. So, okay. Minus, okay. Okay, so let's continue so that we can get for this part, for the red part, you can see we have a common term here and also here, right? So we can just convert it as limit h is 0.0 u of x plus h times limit h minus at approaching 0, h, then v of x plus h minus v of x. Right? We just move the common term out of this one, and then we can just separate into two limits, and then times them together. Then for the second part, it will be limit h is also approaching 0. Then this time we have common term v of x, right? So we just move v of x here times limit h is from 0 u of x plus h minus v of x. So, okay, then the final result we can continue to get. For this part, it will be, because h is 0.0, so here is 0.0, so it will become u of x, right? For this part, times, for this part, it will meet v prime x, right? Did you see? V of x plus h minus v of x over h, when we take its limit, h is 0.0, then we can get the result just like this. Then plus here, because here, okay, what's this term? Limit h is 0.0, v of x, it should be v of x, because you can find, for this term, we cannot find any h, right? So for h is approaching 0, that means for this term, it doesn't regard it as a constant. So just simply move it out, so we can get v of x. Then for this one, we can get v prime x again. So please just keep this formula in your mind. If two terms times together, you want to get its derivative, remember you can just keep the original term first term for first term, but get the derivative for the second term. Then plus keep the original term for the second term, but differentiate the first term. So this is very important. This is very important. Okay, I can give you some. We can just practice that. If you want to differentiate s to the power 1 to the power 2 plus 1 times s to the power 3 plus 3, so that you can regard this is a u, this is a v, right? So we can just differentiate the first term first. So we just differentiate this part first. That will be 2x. We keep the second term. Then the second part is we just differentiate this. It will be 3x to the power 2 times the first term. So the result, through some calculation, you can get the result is just like this. I will skip the detailed calculation, but I believe it is not that hard for you. But here I just want to emphasize that if two terms times together, then if you want to get its derivative, remember, always keep this formula in your mind that we can keep the first term, keep the second term here, we just differentiate the first term. Plus, we just differentiate the second term, but keep the first term. Then finally, you can just do some calculation, you get the result. Okay, So this is about the relative product rule. So if we have the product rule, of course we can find another important rule is rule number 6. That is about quotient rule. The so-called quotient rule is you just face U over V form. For this part, we just encounter U times V form. But for this part, it's about U over V form. So, but for this part, we also can follow the definition to prove it. But since it's a little bit complicated, so I just skip the proof. But I just hope you can just bear the result in your mind that it will be V differentiate U then minus U differentiate V. So a little bit similar to this one, right? But don't forget it's subtraction. Subtraction means you cannot exchange the order. So the sequence, the order is very important. So remember V first times differentiate U first, then minus keep U but differentiate V. So here is V squared. So this is also very hard. And please just also memorize it in your mind, that especially the order. So that means V squared here, and then we just try to not to differentiate V first, but differentiate U first. Then minus U, we will not differentiate it, but then we just differentiate V here. So I will give you an example also, that for example, if you want to differentiate, so it should be T, the example is T squared minus 1 over T squared plus 1. Okay, based on the formula, you can see here is V, here is U, right? So based on the formula, you can get it will be T plus 1 squared here. Then try to not to differentiate. Then you should differentiate V first. So it will be T squared minus 1, right? Here is V. For this part, V squared. Then we should differentiate U first times V. Then minus, we keep T squared minus 1, but differentiate the first term, T squared minus 1 plus 1. And after some calculation, you can simplify it as this result. So I just skip this part. For you, I believe if you can carefully derive it, and finally you can get a result. But remember, when no matter in our quiz or in our examination, midterm examination or final term examination, you cannot use this one. Okay, this is my privilege. Only as a professor can do that. But for you, you need to step by step to finally, and then you can get a result. Okay, so you can tell me, okay, I just suddenly know, okay, is the result is just like this. Okay, I cannot trust that. So please just still follow the step by step. Then finally you can get you can just simplify it as this one. Okay. So then we will go to the rule number 7. Rule number 7 is if m is an integer and n is negative and s cannot be 0, the result will still, when we just differentiate x to the power n, the result still be n times x to the power n minus 1. So you can see rule 7, actually rule 7 is almost the same as rule 2, right? You can see it's also talking about differentiating x to the power n. But the only difference is here n should be positive integer, but here is for negative integer. So that's the only difference. But the result is still the same. The result is still the same. So if we want to prove it, actually it's a very good example for rule number 6. Why I say that? Because if I want to prove it, here n is negative, right? N is a negative. So n here we can just replace it as minus m. Here m will be positive and m is an integer, right? I just simply, because it's a negative, so I just simply move the negative sign here, then keep m as a positive integer. So based on this, we can see if we want to differentiate this one, that will become, we're trying to differentiate this one, right? Because n is equal to negative m. So based on this, we can continue to get it as the 1 over s to the power m, right? So with this form, we can find it will be u over v form, right? With this, v is this one, u is this one, right? So that we can just apply rule number 6 to get a result. So based on this, if you still remember, I may note it down here. If you want to differentiate u over v, it will be v squared over v times du dv dx minus u dv dx, right? So based on this idea, we just follow rule number 6. Then we can get v here is s to the power m, so it will be s to the power of m to the power of 2, right? Because here is v, here is u is a constant. So for this part, we will have v squared. So here we will have x to the power m squared, right? Then we will have v first. So we will have v first, right? Then differentiate 1, right? Because our u here is 1. Then we can have differentiate x to the power m times 1, right? So you can see here, what's the result? What's the result? 0, because rule number 1, right? Here it will be m times x to the power m minus 1. This is rule number 2. Because here m is already a positive integer, so we can follow rule number 2 to get the result will be m times x to the power m minus 1. So that we can continue to simplify the complicated form to become, okay, this will be, because here is 0, so here is 0, 0 times x to the power m, still 0, right? And then we can have minus n times x to the power of m minus 1. Then we have s to the power of 2m. So we can continue to simplify it as 2m minus m times x m minus 1 minus 2m. So we will have minus 1 minus m times x times minus m minus 1. Right? So we can just get back to here is n. Here is also n. So finally we can get n times x to the power m minus 1 back. So you can see, if we want to extend the n from positive integer to negative integer, we need to have the support from rule number 6. Without this, we can get the result. But if we want to extend m to rational number, we still need to rely on another additional rule in the following section. But so far, at least we already extend the n here to be negative integer or positive integer. Two these cases are working for this rule, for that the result will be n times x to the power n minus 1. Okay? Okay, so I give you an example here that y is equal to okay. So if I want to get dy over d, differentiate y, what is the result? So when you just take a look at the function here, you will suddenly decide to use rule number 6. Rule number 6 is about u over v, right? Here is v, here is u. But if you want to rule number 6, the intuitive way is number 6, right? But if you use number 6, you can find it will become a little bit complicated. The calculation will become a little complicated. So why not you just try to explain it to become s to the power 3 minus 2 x to the power 2 minus x squared plus 2x over x to the power 4, right? So that means I will not directly follow rule 6. I just try to explain it. Get the result. And then you can find each item will be an individual term, s to the power minus 1 plus then 3 times s to the power minus 2 plus 2 times x to the power 3. minus 3. So if you want to get the result, then you can simply use rule number 7, because these 3 terms can always have x to the nth form, right? You can see here form n, but n here is negative integer, but it works. So if we want to get the result, we can just simply get minus 1 times x to the power minus 1 minus 1. Then minus 3 times minus 2 times x to the power minus 2 minus 1. Then 2 times minus 3 times x to the power minus 3 minus 1. So after that, we can get the result will be very simple. It will be minus 1 over x squared plus 6 over x3 to the power 3, then this one. So in this case, please just think twice. If you just encounter u over v, is it worse for you to just use the rule number 6? If not, why not just use rule number 7, right? If you can just find it, then you can see each term will be x to some power. Then just follow rule number 7, you can get a result. But if you still can use number 6, I believe the result is also the same, but the form may be look not that similar. Okay, so maybe let's just take a break, then come back to the classroom later. We already know these 7 rules. So in the future, if you want to calculate the derivative, you can directly apply these 7 rules to get the result. Okay? Then that means you don't need to go back to the original definition. You can just simply apply these 7 rules. But if we emphasize that you need to use the original definition, you cannot just simply use these 7 rules. Okay? Because sometimes, as I told you, I hope you can have a real experience in using the original definition. So if in the question we just emphasize that you cannot use the application, the derivative rules, please just follow the original definition. OK， 就是考试的时候，假如我们有特别强调哈，就是说你不能用这个微分公式哈，那你就要回到原始的什么 limit h 趋近零 f of x 加 h 减掉 f of x 除以 h 去推导或者你可以用 limit z 趋近于z 趋近于 x f of z 减掉 f of x 除以 x z 减掉 f of x z 减掉 x。如果有特别强调说你就不能这样做就是主要是原因是什么？我说过要让大家真实去体会它原始的定义了，因为到最后有了公式就不会去用它原来的这个定理，的定义我觉得有点可惜那就好像我常常举例的就是说你现在有脚踏车有汽车有摩托车，你就不见得会喜欢用走路的方式，对不对？或者你现在有 AI， 对不对？有 Chat-GPT， 你可能就对了，还有考试的时候不能带手机不能开手机因为现在这个 Chat-GPT 太厉害了，所以我们都是而且不会需要用到什么复杂计算放心好了，你不用带什么说要带什么工程计算机，不用，不会有那么复杂的这礼拜3的时候可以，但真的不会了不用带，真的很简单，就是2加3等于5，你还用计算机那可以带最多什么有没有？上面这 n 减1啊 ，n 减1你不会吗？5减1等于4这样就是这种程度而已，好不好？真的用不着了杀鸡焉用牛刀。 Okay, so let's continue. So before I just finalize this section, then I will talk about the higher order derivative. So just like in the past, we just learned f prime x, right? This is the first order. So when we just talk about higher order, that means more than uh, uh, get the derivative twice. So that we are talking about the f prime x, or even f triple prime x, or even f. Sometimes we will use this to show the higher order. So for this, that means we just differentiate f prime x. Then when we get the first order f prime x, then we just differentiate again. Then we can get f double prime x. So you can just follow the same rule. We can get this one by differentiate this one. So that also means that we just differentiate this one. That also means that we try to differentiate it 3 times. Okay. So I believe you also can, for you, it's easy for you to understand that we try to differentiate. We just use the recursion to define if you want to get an order derivative, then you can just differentiate n minus 1 order derivative. We get the n minus 1 order derivative first, and then we differentiate it, and then we can get an order derivative. So I think that is not hard, right? Then this is about section 3. Okay, then we will move to section 4. The derivative as a rate of change. Actually, we already repeat the concept several times. Derivative actually is just same as the rate of change. We already repeat this concept, right? So next time we talk about this derivative as what? As instantaneous rate of change. Right? Before we reach this concept, we just talk about the average rate of change. But as h is a 0.0, then we can suddenly get the instantaneous rate of change, right? So at that time, we also talk about that f prime x should be defined as limit h is 0, f of x plus h minus f of x over h, right? So at that time, I told you that this part we talk about the average rate of change in some certain interval, right? But as h is getting smaller and smaller, and even h is just become 0, touch to 0, very close to 0, then we will get the instantaneous rate of change. But at that time, we just focus on like the function will be defined in terms of t, time, right? T means time, right? But it's not always, the function is not always defined in terms of time. It can be in terms of another physical factor. So, for example, I will give you an example that how fast does the area change with respect to the diameter when the diameter is 10 meter. Okay, so please just look into these questions that you can see. This question just asking that the area change with respect to the diameter. So, or we may know that for a circle, for a circle, the area will be depends on the diameter. Diameter means here, right? This is the area, this is the circle, this is the diameter, right? So the area, the whole area, supposedly should be A is equal to pi times, this is when we just divide diameter by 2, that means this is a radius, right? This is a diameter, this is a radius. I mean, this term is radius. Then it's square. So this is the formula for which I want to calculate its area for a circle. So you can see, you can regard A. So you can regard A as a function of D, right? Area will be determined by some function in terms of D. D here is the diameter. So you can regard D is an independent variable and A is a dependent variable, right? So in the past, we always illustrate a lot of examples that the function is determined by X or determined by T. Normal T means time. But for some application, if we want to get the area, especially for a circle, then we can formulate as A is equal to f of D. Then f here will be here. We can just formulate is A is equal to pi over 4 D squared, right? So we can see D determine A, right? Only D, one single variable, can determine A, because for pi, for 4, they are constant. They will not affect A because this is a constant. They will not be changed. But D is possibly changed, right? So for example, if your circle become bigger, that means that D is become larger, right? So this, for example, this is another D. This is D1, this is D2. D2 is much larger than D1. So we can always find D can determine the area. So when we just differentiate A in terms of D, right? So that means we are trying to look at the with a very small change in terms of D, how much area will be changed in A? Let me just emphasize it again. So this expression is just talking about it. How with a very small change in D, small d with a big D here, we will see how much area in A here will be changed. So based on this, we can see the result will be, if we just differentiate, we can get that will be d over dd pi over 4 d squared. So we can get the result will be 2 pi times d. So you can see another idea through this formula, through this expression. So that means the changing rate will be determined by d, but the area size will be changed. It will be determined by d squared. It's different because d squared will determine the size of the area, but d will determine how much the changing rate. Okay, so when we say d is 10 m, so the area is changed at pi over 2 times d, 10, that will become 5 pi. Then the result will be m squared over m. Why I emphasize m squared over m? That's very important. That means per meter change, it will cause 5 pi area change in meter squared. So please don't say you can just cancel it. No, you cannot do it. This m squared over m means how much small change in the diameter will affect your area change. So per meter, you will cause 5 pi meter square change when diameter is 10. So, but for example, if d is 1 meter, so the changing rate will become pi over 2 times 1. So that will become 0.5 pi meter square m. So you can have a simple comparison that this is for d is 10 meter. So you can see this is, for example, this is 10 meter. If this is 1 meter, right? So this one is here, this one is here. So per meter change, you can see per meter change, their changing rate is different. That will based on how long is your diameter. So you can see here, if we just add additional 1 meter, okay, maybe 1 meter is too much, but for example, additional 0.1 meter, so you will cause the area change is like this one, right? But if you just follow the same idea that you just extend 1.1 meter, you can just cause a differentiation change here. So you can make a simple comparison. This one is much smaller than this one. They will base on your diameter. So for 10 meter, the changing rate is much bigger than this one. OK？ 哦，这边要有一个很重要的澄清哈，就是说，这观念很重要哈，就是你会发现哦，我们本来这个圆面积的公式啊，事实上是 a 等于这个半径的平方乘以派，或者直径除以2的平方乘以派，这是在算面积大小哦。但是呢，当我们因为面积呢，事实上取决于你的直径或者是半径，看题目怎么给哦。直径、半径都一样，就是不管是直径或半径，它都会影响到你的面积大小。但是我们在讨论 dA 除以 d， 就是对 a 微分的时候，我们在讨论一个什么观念？就是你在一个很小的半径也好，或直径的变化之下呢，会引发出多大的面积的改变量。所以这个公式跟这个微分的公式，它所探讨的物理量是不一样的东西。一个是表示你现实的这个面积大小是多大，这个是在讨论当你有1公分、10公分、100公分或者1公尺、2公尺的变化量的时候，你的面积会有多大的改变？那这个是在讲这个的变化量。好，如果把微分出来的时候，这个题目实际上到这里就结束了。但是这个题目为什么我要再延伸再讲，让大家做个比较，是在于，你看它如果是10公尺的，它每增加一点点，哦，因为这个增加量都假设是一点点，比方固定的是 0.1。如果今天是对一个10公尺直径的圆，跟一个对1公尺直径的圆，当你增加都是增加 0.1 的这个量哦，你会发现哦，它增加出来的虽然大家都是增加 0.1 哦，等于说直径上你就增加 0.2 了哦，这个画起来看起来像是半径增加 0.1， 直径增加 0.2， 直径增加 0.2， 对这个 case 来讲，大家都是增加 0.2， 对这个 case 也是增加 0.2 的直径。可是你会发现，它增加出来的这个物理量大小就不一样。这也就是你会发现10公尺的圆跟1公尺的圆，当他们在考虑这个增加，在一个固定的微小的低的增加量的情况之下，它所引发出来的面积的增加量事实上不一样的。一个是什么？5拍米平方除以米，这个注意这个米跟米不能消掉，这个一个是讲的是直径上面增加的多少公尺的长度，引发出来你多少面积的增加。所以这个意思是每公尺增加了多少平方公尺的面积。所以这个单位一定要这样写它不是说米跟米可以抵消一个，不是一个是讲的是长度，一个是讲的是面积。所以如果你看看它如果是10公尺的时候，它是每增加1公尺，每公尺它可以增加5拍的米平方的面积量。可是如果你的圆的基础很小，只有1公尺的这个直径的话，同样在每公尺的增加我讲的是那个直径的增加量之下，你会发现它的面积增加量只有 0.5 拍。那这也很合理，看这个图，这张图就知道，它的原本的直径也好，或说是半径也好，它本来就是比较小的圆，所以当你增加一个固定的这个长度在它的直径或半径上面，它所引发出来的增加量呢，事实上不弱这个原始的圆，它长度比较长，它的直径比较长，或半径比较长，所增加量，即便它们两个都只是扩增了 0.1， 这样了解我的意思吗？就是它这个本钱比较粗了，这个本钱比较小，所以增加一样的量的时候，它跑出来的 结果呢，增加量就不太一样啊。那这是很重要的概念哈，同时单位也非常重要啊。Okay, actually, in our textbook, our textbook also illustrates some example in physics. So I can give you some example that, like in our textbook, we also talk about the motion. We also talk about the motion along a line. So originally, the displacement can be defined as f of t. So normally t here is a time, then s is a displacement. So this is the function of time for motion. Then we just use t as its variable. Then we also define displacement. We say delta x. When your time is running from t plus delta t to f of t. So that means we are trying to find the displacement when your object, when the object is at time t to time t plus delta t. So once we calculate its difference, we can get its displacement. Then we continue to get the average displacement. If you want to get that, we just simply use delta s divided by delta t. So that means it will become delta t over f of t plus delta t minus f of t over delta t, right? So for example, maybe the time is 5 minutes. So from now and after 5 minutes later, you can calculate its displacement, and we can also get its average displacement. Then we can furthermore to discuss its velocity. For velocity, we will say it's an instantaneous velocity. Then we will say it will be v of t. We will define it as ds over dt. So that means we are talking about limit delta t is approaching 0, f of t plus delta t minus f of t delta t. So you can see that this is the average change. This is the average change for the motion. This is the instantaneous change of rate for the motion. But you can see here and also here, you can see for instantaneous, we will force its delta t is approaching 0. But for the average part, we will consider a certain amount of difference in t. So based on this, I believe you also learn from your physics that normally we will have ST diagram that we are described S of t just like this. If we say ds over dt is positive, that means S is increasing. then in this case, we will say this is moving forward. Right? But in another case, another ST diagram, if the figure is just like this, that means ds over dt is negative. You can see as time goes by from here to here, for example, 5 minutes, 10 minutes, so we can have a 5 minute difference. But for its distance, its displacement, it will be negative because from further to become near, will be closer, right? So it is a negative. When we just differentiate, then S will be decreasing. Then we will say this is moving backward. But normally when we just talk about speed, we don't care about its direction. So for speed, we will define it as Vt, taking its absolute value, then we will say it's ds over dt. So this is an example about, this is another example. But this example is much intuitive because, you know, when you just study physics, motion is a very important part, right? So you can easily to find how to apply the derivative idea to get the derivative for some motion for the object. But don't forget, we also can formulate some amount based on some another factor, like when we just want to calculate the area size in terms of the diameter or in terms of the radius, you always can formulate that like this. For motion, I think a lot of cases you already encounter. So I think that is not that hard for you to understand the idea by applying the derivative to get its speed or its velocity. And the last one I want to show you is how can we just apply the derivative in economic. For economic, I want to use an example for you that for the horizontal line is about how many units, for example, x units. For the y-axis, we are talking about its cost. So when we just model it, we model it the cost as a function of y is equal to c of x. So we talk about the cost function of production. So you know, when we just making some things like making shoes, the factory, the owner of factory need to pay some money to make the shoes, not just use the money to buy the materials. The factory owner also need to build a factory, right? So it's about the cost, right? So we can model it as c of x as a cost function, the cost function. So for example, the cost function is just like this, right? If you want to produce more units, you need to buy more materials. You need to buy more material, you need to pay more money, right? So as the x is going up, then your cost will be continuously be increasing, right? But as you manufacture more products, the cost will gradually become very stable, right? So for example, if we want to ask you about that, when you just manufacture S units, then the cost will be here, right? This is a C of X. But if you just produce additional h unit. Then here is x plus h. So the cost may become x plus h. Right? Then if we want to calculate the distance, the difference, that will be c of x plus h minus of cx, then over h, right? So that you can get the average. So you can get the average cost of production of additional H products, right? Original, if you just want to produce X products, the cost is here. If you want to produce additional X unit, here will become X plus H. So the corresponding cost will become C of X plus H. So when you just get its difference over H, then you will get the average cost of production for the additional H, right? This is additional H. So if we try to differentiate it, if C of x is a differentiable function, so we need to assume C of x is a differentiable function, then we are talking about limit h is 0.0 c x plus h minus c of x over h, right? So sometimes we also call it a marginal cost. Marginal cost means when you just want to produce H additional H products, how much you need to pay. What is the average cost? Then we will say it's a marginal cost. So sometimes, but you know, shoe, how many shoes? It will be a discrete problem. It's not a continuous problem. So we only say, okay, you have one pair of shoes, two pairs of shoes. You will not say 0.5, 0.1 pair of shoes, right? For shoes, it must be a complete one. You cannot just buy shoes from like 0.5, 0.6, right? It always should be an integer. The among numbers should be an integer. So sometimes the margin cost marginal cost of the production can be loosely defined to be the extra cost of producing one unit. So that will become delta C over delta X will be C of X plus 1 minus C of X over 1. Because delta X cannot less than 1. Because it must always be integer, right? From two pairs of shoes to 10 pairs of shoes, so they will 8. 2 to 9, they will be 7, right? 2 to 3, it will be 1. We cannot have 2 to 2. 2 to 2 is just you just stay the same, right? So normally we will consider additional 1 as your marginal cost。这边呢，其实我们重点不是在讲这个经济学只要跟大家 勾勒一个概念，就是说微积分其实微分积分积分后面我们才讲。微分的时候呢，事实上我们对的是一个连续函数的处理，对不对？我们是在处理什么？它的dx 很小的时候，我们去看它的 df 的变化量。可是往往在现实条件里面呢，我们没有办法对这种所谓的离散的世界做这样的一个计算通常就拿我们的鞋子好了，我们的车子好了，我们的桌子好了，我们没办法去做什么 delta 这 h 趋近零这样的一个动作。为什么？因为趋近零这个动作事实上是在连续函数的条件之下可以做的，可是在离散的环境里面你没办法做这样的事情那当然在 idea 里就是比较理想化的情况之下，它如果是一个连续函数是可以模型化的。就好像我记得第一堂课的时候我跟大家讲过一个概念，就是我们在算那果蝇的时候，果蝇你有去算那 0.3 只的吗？ 0.3 是不能活了对不对？鞋子你有去买一个 0.5 只的吗？ 0.5 双的吗？ 0.5 双可能你的左脚被人家偷了，去买一个左脚回来左边的鞋子。但我要讲的是说，这个是一个玩笑话，当然你不可能去买一个0.多少双的鞋子，对不对？所以在经济学上面的时候，但我不是经济学家，但是我说如果我们要 apply 我们的微积分上去的时候，事实上它通常是做什么事情？它通常是在帮你 model， 我们会有一些离散的点，比方说我做10双的时候的成本是多少，11双的时候成本是多少，所以我们在连续函数的呈现上的时候，我们会拿这些离散的点去模拟出它的连续的曲线，因为只有连续曲线可以做微分，对不对？离散的点是没办法去做微分的，所以我们必须 sampling 取一些离散的点。那通过在有一门学科叫做数值分析，叫做 curve fitting， 我可以去用一个 curve 去模拟这个你经过的这些点。所以大家应该有听过 linear regression， 有没有？线性这个回归，对不对？还有多变数的回归，对不对？那线性回归里面就是很简单的，就是我经过某几个点，我可不可以用一个很简单的曲线去模拟它？那得到这种曲线之后有什么好处？我就可以去微分，我可以微分，我就可以知道在某一个物理量的那个当下它的变化量有多少，不然你是没办法做到的，对不对？好，那终归它是模拟嘛。但如果回到现实条件里面，我们要做的是一个什么？是一个离散的环境的模拟。说我的瞬间变化量的时候，我们通常怎么做？我们去定义了一个叫做所谓的这个 marginal cost， 这个叫做边际的成本嘛。所以边际成本事实上是说，如果我从 X 双的鞋子的生产的成本进展到我生产 X 加 H 双的成本的时候是多少的时候，这个我们算出来除以 H 之后，我就可以知道说，我从10双生产到20双，10双到20双的时候，它不一定是线性的为什么？因为我们知道机器可以摊提嘛，你今天买一台机器100万，就为了生产1双，那你的成本那就100万，对不对？可是如果你生产出10双，它就帮你摊提掉了，对不对？那大量生产的时候，那摊提的更明显，所以你会发现，永远在成本上永远会比较趋缓的趋势。所以这时候，如果我从 X 双生产到 X 加 H 双的时候，我势必成本上会增加，但是不会那么线性，因为我说过机器可以共用，机器可以重复使用，机器的费用可以被这些额外增加出来的做摊提。所以呢，当我生产到 X 加 H 双的时候，势必会有另外 cost 出来，我就把它两个相减除 H 的时候，这个我称之为额外 H 个产品的时候所得到的平均的生产成本。这个结果呢，跟你 X 到 X 加 H 里面呢，从10到100，跟你到1万又10双到1万到100双 这个曲线绝对不会一样。这我们后面在讲那linearization的时候就会讲到这个概念，因为它的平稳度会不太一样哦。特别是你在一开始的时候，因为你的成本一定摊提的比较高哦，所以你这边的曲线会特别的陡。那在这种情况之下呢，如果我没办法做到 H 双的这种，其实如果我真的想要做趋近于零的这样的动作，通常我做不到嘛，你不可能有真的趋近于零双的这样的一个条件出来。那如果在离散时间要怎么做呢？我就勉为其难的，就是说起码至少我要有一双，所以通常呢，我们会就利用强迫在 H 只有1的时候，我们去算出它的 marginal cost， 它的边际的一个额外的成本，我们是利用这个来计算。那当然这是经济学家在弄的所以最后呢，还有一点时间OK， 哇 ，we just have less than 1 minute。This I just prepare two less slices. Uh-oh. Okay. Sorry. Where is my eraser? Oh, here. Okay, I got it. I need a break one, but originally I need to have more blank slices, but I don't know. This time I just prepare two less. So I just use the very straightforward one to get a break. Okay, maybe let me just spend one additional 1 minute to tell you the idea. The idea is very simple, so please just allow me to give you one additional idea that we are talking about the sensitivity. Maybe next time I will tell you the detail, but you already have the idea, so I want to skip it. So when we talk about the sensitivity of change, we are talking about when a small change in X changes. Can we just produce a large change? Did you know the butterfly effect? 蝴蝶效应有没有？什么叫蝴蝶效应？他说在什么太平洋一个蝴蝶这边拍，结果就在哪个地方就造成它那个很大的这个什么飓风有没有？所以 when we talk about the sensitivity of change, we are talking about if a small change can produce a large change in the value of a function. No worry, this part is just a concept about derivative. So we will say, in this case, we will say that the function is relatively sensitive to change in X. So that means if you can have a small change in X, you can produce a lot of change in f of X. That means the function is very sensitive. And how to evaluate the sensitive? The derivative at prime X is a major way, is a measurement of the sensitivity. So that means if we want to know sensitivity, okay, if you want to know how sensitive the function is, you can just get its derivative. So for example, one function its original one is y is equal to 2p squared p minus p squared. Then you can see at this moment, very close to 0, the change, if you have a small change in p here, you can get such kind of change. But here, if you have the same small change, you just get a very small change here, very small. So green one is much smaller than the yellow one, but with the same change. So you can see here the sensitivity is much less than here. So how can we just know that? We can just simply, for example, here is y, we can just get dy over dp. Here is still p. You can see here is so large, but here is so small. Right here is so small. So based on this, you can know its sensitivity. So no worry. This part is I just want to talk to you. We can just use the derivative to measure the function's sensitivity. So it's also an application of derivative. Okay, so this is for the section 4. But I don't think this part is very hard for you to understand. So please just also have some practice when you go back to home. Go back to your home. But remember, this Wednesday we will have a quiz. And the range, I believe we already announced that, right? And the question, we will have, I remember maybe 10 questions. But that is not that hard. But that is not hard doesn't mean you don't need to study. Okay? So please just well prepared for the quiz. Okay? See you.